Well, thanks very much for the opportunity to tell you a little bit about what we're doing 2 kilometers underground. My role here is to try and give you a flavor of the science we're doing. And we'll see if we can get this thing to work. And I was told by the instructors not to turn around and look at the slides. Apparently my head's too shiny for the lights around here. So, a couple of months ago, I happened to be delivering some lectures at a school for graduate students in India. And at the beginning of that series of lectures, the director of the facility stood up to introduce the school, as it were. And he was a big, imposing scientist from India. And he stood out there and he put his hands on the hips and he just stared until every single student was dead quiet and you could hear a pin drop in that room. And then he started his speech, which began, "Twinkle, twinkle, little star, how I wonder what you are." And I thought that was really, really fascinating. If you look at this picture, I think it embodies what I find exciting about science and what he also found exciting about science, this sense of wonderment. Right? When we're little kids, the stars are just fascinating to us. When I look at this picture, I wonder, what on earth created that marble arch? What is going on with this light show that gives this interesting sunset? And then you see the stars, you see the Milky Way, there's galaxies, all kinds of fascinating things there. That's what really drives science, I think, is a sense of wonderment. Of course, as time has gone on, we've developed our tools. That last picture had a few stars, it looked kind of cool. You now shine the Hubble telescope and you get images like this, where you see this fascinating mosaic of events and stars and all kinds of interesting things going on in the cosmos. And it really does generate a lot of questions. So we are fascinated with the cosmos, as I said, and for good reason. If this video works, and it doesn't work there, it works there, good. So this is a supernova, right? This is one of the most massive, explosive things that can happen in the universe. And it turns out that when a supernova goes off, that's how we actually produce many of the materials that we are made of. Anything bigger than iron, lead, iodine, things that are in your body, gold, silver that you wrap around your fingers, all of this was made inside a supernova. So we are actually composed of this second generation stellar dust. Right? We used to be the inside of some star that long since exploded, recollected all that debris and formed us. Okay, so I think one of the points I want to make is that basic science is really driven by this curiosity. Right? And in doing, forming the questions that you have passions about leads to research. That research leads to solutions, but it also leads to new technologies that you have to develop in order to do the research you want to do. And that new technology has all kinds of interesting spin-offs, and gives us, of course, a better understanding of the science we're trying to do. So why on earth would we do science underground? 2 kilometers underground, what I want to do is study the stars in the sky. And I want to do that 2 kilometers underground. Sounds a bit crazy, and it turns out you're not the first people maybe to think that. There's this quote from Pliny the Elder, it goes back about 2,000 years, where he said this in Italian, which if you translate it to English, says roughly that there are those people who are so foolish and crazy that they would go to the bottom of a mine to study the stars in the sky. And that's exactly what we do. And so I'll let you be the judge afterwards. He was trying to find a definition for crazy, in fact, and that was the best he could do. So you can be the judge. Okay, so why do we go underground? Actually, the problem is, as we sit here, we have the sun not too far away, and there are streams of particles coming out from the sun continuously, these cosmic rays, and they are raining down. Fortunately, we have a very strong magnetic field. Most of them are diverted around the Earth, but some of them penetrate. You've all seen the northern lights, brilliant displays when you have a lot of sun activity and you get more particles than normal. We also get cosmic rays that are very energetic coming from other stars elsewhere in the galaxy, and this is a problem. The problem is that when they hit the atmosphere, they have collisions with the nitrogen and the oxygen. They have a lot of energy, E equals mc squared, that can produce other particles by creating more mass. And you have this cloud of particles, this huge shower raining down on us all the time. If you've ever lay on a beach with your eyes closed, but you're still awake, and you've seen these flashes of light in your eyes, these are charged particles going through your eyes. These are the cosmic rays. If we put our experiment on the surface of the Earth, we wouldn't have a hope of seeing the very rare interactions we're looking for. And so what we do is we go 2 kilometers underground. Now, fortunately, Canada has the deepest mines in the Northern Hemisphere. We found in the Vallée mine, we were able to find a spot where they were very open to us putting our experiments there. And so we go down 2 kilometers, we walk in another 1.5 kilometers, and we get to our laboratory. The whole purpose is to use that 2 kilometers of rock to filter out all of those cosmic rays. And it turns out we're the deepest mine, which gives us the greatest advantage in terms of reducing those backgrounds. Okay, so this is a little bit what the lab looks like today. It's just a labyrinth of underground tunnels with these huge halls. And some of those halls are the size of 10-story buildings, right, where we build our detectors inside those halls. And we have 3 large halls and many smaller halls where we put more modest-sized experiments. Just to give you a flavor of the scale, so this was one of my classes, actually, I took up for a trip. And we went underground. It was just after we finished building this hall, so there's nothing in it yet, but it gives you a sense of the scale. The original experiment that we had there was called SNOW. It was the Sudbury Neutrino Observatory. I'll tell you a little bit more about that. It just crammed into this cavern, and that was about 10 stories tall. And the only way to get in there now is, kind of tricky. You have to lower yourself down on a rope through the neck of this thing until you get inside the detector. And so if you can look up, you see this guy coming down on a rope. Okay, so what are the things we're trying to address in this facility? We have a lot of things we want to do. First of all, there's something I'll tell you about called neutrinos. Very elusive particles. We didn't know anything about them for the longest time, and we can study them underground because we can get away from these other backgrounds. There's something called dark matter, which I'll also tell you about, which this matter that pervades the universe that we really know nothing about, and it's everywhere, and we'd like to see it and understand it, so we can do that underground. We're trying to study what happens in supernovas. What is the process that actually built all the material in the universe? We know we began with the Big Bang with matter and antimatter in equal amounts. That's all annihilated now, except it turns out there is some strange asymmetry at the beginning. And all that's left now is the matter. That's what makes up our universe. 1 part in a billion left over. Trying to understand the physics of why that is. There are other people who come and use our lab because they want to understand biology. Who knew that there is more mass contained in the rock under our feet than there is above the surface? Just because, of course, you've got kilometers of rock where you can populate it with all these bacteria and so on. So there's lots of interesting things to do. But before I get too much into the physics, I have to just remind you a little bit about the basic constituents of matter. So we were supplied with a little bit too much of this last night by the hosts. That's your basic ordinary matter. If you were to look inside, you'd find the most important ingredients, water, and of course, ethanol. If you looked a little closer at the ethanol, you'd see, well, in fact, every one of those carbon and hydrogen is a little atom. And for the longest time, we thought that was all that there was, electron going around some nucleus. But now we know if you look more closely at the nucleus, there's neutrons, there's protons that make up the nucleus. If you look even more closely, you see inside there are the quarks. And we think at the moment that that's all there is. And in fact, there's reason to believe that, in part because we can now build these exquisite models that use only these particles. So this is the entire family of particles that you can build everything in the universe and controls all the forces in the universe as well. Now, for the most part, all you have to care about are these 3. Up and down quark, they make up all normal matter, and the electrons. There are heavier brothers to those you see, like the charm, the strange, the top and the bottom, but they're all more massive. They decay quickly back to the others. The electron, you know, and its bigger brothers. Of course, the other thing is they interact with each other some way. And the one you're most familiar with is the electromagnetic force. I can't put my foot through the ground here because the electrons in the ground push back on the electrons in my shoe. That's the electromagnetic force, and you're all familiar with a photon, which is what mediates that force. Yeah, but there are other forces. And then there's the neutrinos that I want to talk about. And just for this, we'll go in more detail what they are, but for now, just remember there are 3 types of neutrinos. Okay, so neutrinos, what are they? They're extremely light. We thought they were 0 for a long time. They're extremely abundant, and what was my other point? Very weakly interacting. So if you look at your thumbnail, there's roughly 1 billion neutrinos going through your thumb every second. They're just a huge number of neutrinos. The problem is they go right through your thumb, they go right through the Earth. In fact, a typical neutrino will go through 4 light years. That's 4 light years of solid lead before it has a single chance of interacting. Right? So they're very difficult to detect. However, we started off with this program at Sudbury where we were trying to solve a problem which had persisted for 30 years. And the problem was you could calculate how many neutrinos you thought were coming from the sun. That's my 6 arrows there. And every experiment, and many of them, for 30 years discovered there's only about a third of what we expect. And so there was clearly something wrong. Either we can't do fusion reaction calculations or something about the neutrino. So we built the Sudbury Neutrino Observatory to explore exactly this. And we had a theory that maybe what's happening is the neutrinos, as they come out, undergo some weird quantum mechanical effect, and they change from the type of neutrino that's made in the sun to some other flavors. Remember, I told you there were 3. And so that's what this depicts. And what we found is if we only measured those neutrinos that we thought were made in the sun, we got the same answer as every other experiment, 1/3. But we had another reaction we could use, which measured all neutrinos independent of what type they were. And what we discovered when we did that is that we saw the full flux. All the neutrinos were there, but indeed, the other experiments were blind to those other flavors. They could only see the ones made in the sun. And so that was a problem. So we knew now that very strange things were happening. Inside the sun, the neutrinos were flipping from one flavor to another through some quantum mechanical effect. Okay, interesting physics. Why is that interesting? In part, it's interesting because they can only do that if they have a mass. And we thought they didn't have any mass. If they have a mass, then they affect gravity, or they have a gravitational effect on how galaxies form, how structure in the universe forms. And so we had to revise all that. We know that the universe is expanding at the moment. It's an open question, it had been an open question, of whether it would continue to expand forever, or whether perhaps gravity would start to collect everything up and it would all come back together in what we call the Big Crunch. In standard models of cosmology with what we know about the neutrino now, it seems like there will not be a big crunch. We will become a very cold and an empty, desolate universe. The other thing was that if the neutrinos had mass, then maybe they were responsible for all this other matter that we've been curious about, what we call the dark matter. And so it turns out that's not the case. They don't have enough mass to do that, but that has led us nonetheless onto doing more pursuits looking for dark matter. So this is a pie graph which tells us what we know about the universe in terms of the matter and energy budget, and it's kind of embarrassing. We know 5% of the content of the universe. That's it, 5%. And most of that 5% is dust in the form of gas. Less than 1% of the entire content of the universe is held in the mass of stars. There's this dark matter, which I'll tell you about, which is 25% of the content of the universe. And this dark energy, which I won't talk about, but this is an energy where not only is the universe appearing to expand, it's accelerating in that expansion. Something is pushing it faster and faster and faster away from itself. And that's some kind of energy, which we call dark energy. Okay, so how can I prove to you? There are many different ways that we understand that dark matter exists by looking at the cosmological and astronomy observations. But this one is fairly simple to understand. And it's if you look at a galaxy and you measure the velocity of the stars, and what you would expect is that if a star is on the outside, if it is way, way away from the center of the galaxy and it's going too fast, it's just going to get flung out of the galaxy, right? Not so different from if you look at a typical roundabout. Well, you don't see these as much any days. But if you're on a roundabout, you see all the kids holding on to the roundabout. The ones on the outside are all holding on. The kids on the inside are not holding on, right? If you spun that fast enough, you'd fling all the kids on the outside off, right? If you spun it really fast, you might get them all. But the point is, that if you get on this galaxy, if the stars on the outside have enough velocity, they should be flung out of the galaxy unless there's some force holding them in. There's not enough force with the gravity we can account for, so there has to be something else. And that's this evidence for the existence of this whole thing being embedded in dark matter. And there are many, many other ones, but this one is quite a visual way to see things. Okay, so how would you detect dark matter if you wanted to? What you're looking for is this dark matter particle comes along, and it flies through some target that you put in the way, and it knocks out the nucleus. And the nucleus carries away a little bit of energy. So now your problem is just to measure a tiny amount of energy. You might measure it through heat. You might measure it through a light flash or something like that, or maybe even from the ions that it produces. But that's what you're after, and it's a tiny amount of energy. So your detector has to be incredibly sensitive. That's one of the big challenges. Not only that, your detector has to be extremely large because the probability of these things, you might get one event every year in a ton-sized detector. That's why you build your megatons, if you could, size detectors, and why the lab is so large. And you have to be patient. The other problem is radioactivity. Anything that might mimic the signal and look like what you're looking for but is actually from radioactivity is a problem. So if any of you were to stand 2 meters away from my detector, the signal would be 10,000 times higher than what I'm looking for because you're full of potassium. Potassium is radioactive. You're all hot, basically. Okay? Another example of what the sort of extremes you have to go through. This is a picture of some divers for not one of our experiments for quarry. You'd think, okay, if you've got radioactivity, let's wrap it with lead, right? That's what your X-ray technician does, puts a lead apron on. Well, the problem is that lead itself is radioactive. But if you could find lead that was made thousands of years ago, that lead is now that radioactive part is decayed away. And so these divers are going down to get the old lead bricks that were used as ballasts in Spanish galleons and collecting it off the seafloor and making their shields out of that lead. So those are just to give you a flavor of how hard it is to make these experiments work. Okay, so here's a detector we're actually designing, just to give you a feel for what one of these things might look like. This one's kind of unique. The same idea, though. Dark matter particle comes in, and it hits our detector. Now, this detector is superheated fluid, which means it's above its boiling point. It would really love to be boiling, but it needs some kind of trigger. Well, that trigger could be the little bit of heat that's deposited by this dark matter. Right? When that heat forms, you get it starts to boil right where that heat is, so you get a little bubble. And you actually can see the bubble form with your cameras. So we often joke that we might see a couple of events like this per year. We are video recording all the time. This has got to be the most boring movie on the planet. Right? When the bubble forms, though, it also makes a nice pop sound. You can hear it. And so our eyes are these microphones and the camera. So here's some examples of some pictures. In one case, it was on the surface. You can see a cosmic ray going right through the detector. Another case, one of our problems is neutrons. Neutron got in there and it bounced around. It formed many bubbles. And what we're looking for is the last one, which is a single bubble in the detector. Okay? And when these bubbles form, you get this, which is your microphone trace. Okay, so that's what we're looking for dark matter. The other thing I mentioned was supernovas. So supernovas are very complicated beasts, many different types, many different mechanisms. But the basic idea is when the star is in equilibrium, gravity is pulling everything in, but because of the fuel burning process, there is energy streaming out, particles streaming out, and that keeps the whole thing balanced. When you turn off that furnace, so you're no longer burning energy anymore, then suddenly all you've got is a gravitation, and immediately everything starts to collapse inwards. And when that happens, you can form either a black hole or maybe a neutron star. But the important thing is all this material falls in, and then it rebounds. And you get this enormous shock wave as the stuff that all came in suddenly compresses and bounces back out. And that throws all this debris out into outer space. And that's what this picture is. This is a Crab Nebula, which was seen by scientists over 1,000 years ago in China. This is what it looks like now. Still a lot of light as that stuff is spreading out through space. But the initial thing is only a matter of seconds. And what comes out most is neutrinos. They stream out of this thing like mad. In fact, it takes the light quite a long time to get out. So what do we learn? Well, we can use those neutrinos because they come right from the center of the core where the physics is happening, and that tells us about what's happening inside a supernova. The light only comes from the surface, and it comes quite a bit later after the star is big enough in this explosion, it's not so dense that the light isn't just bouncing around inside. So we can actually call our friend Bob, and say, look, Bob, there's a bunch of neutrinos we've seen. We know there's going to be a supernova up in Cygnus. We recommend you turn your Hubble telescope around and have a look. And that's what happens, right? They will only be alerted some hours after the neutrinos will start to get the light coming. So it's a way of coupling those two communities and learning a lot about supernovas. Okay. So let me just finish about where we're going. So in a supernova, it's a long, slow process, but eventually you get this very dramatic finale, this gigantic explosion, which is very informative and very spectacular. But in fact, it's not the end of a process at all. In a supernova, first of all, we are generating all the material that made the Earth and made ourselves. And in a supernova, when you get this shock wave going out and it goes through all that dust that I told you about, which is hydrogen gas, it actually seeds the formation of new stars. And so, although it's the end of that star, it's a process that begins again. And I find that that's actually not so different from where we're going scientifically. Right? We have this initial idea, and I believe science done properly should be basic science, which is driven by your passion and your curiosity. You get an idea, you run with that idea, you have to get money and support, you get industry and government agencies on board and all that sort of stuff. And then there's a long period which usually ends up with a very informative result. It might be a spectacular result, but it's certainly not the end. Right? It generates new questions that we would like to explore. And I think, you know, for me at least, that's really what should be driving science. It's this passion-driven science, new ideas, and you just follow your heart. So thank you very much.